Okay, we start shortly. Yeah. Okay. Get started. Hello, welcome everyone. This is the first Rollo Davidson Lecture, and it's a really special year because this year would mark the 80th anniversary of Rollo Davidson's birth. Of course, it's particularly special because we have a very special speaker today, Allan Sly. Allan had a very interest in mathematics. He participated in the international Olympiads and he earned a silver medal. At Australian National University, where he got a bachelor's in math degree, and moved to Berkeley, where he got his PhD in Canada Morrison. After that, he spent some time as a researcher at Microsoft Research, and went back to statistics department at Berkeley, and then joined Princeton, where he is now HP Lee 79 Professor of Mathematics. Is that right?
Yep.
Okay. Allan is a very distinguished and influential probabilist, one of the leading probabilists in the world today. Worked on a very broad range of topics, including questions in core probability theory, as well as problems that arise in theoretical computer science, some physics, and even theoretical statistics. Have been very broadly recognized. He has he's been a Sloan Fellow, a Dartmouth Fellow, recently got the Love Prize, and most importantly, he's also received the Rollo Davidson. Right, so it's a great pleasure to welcome Allan. Thank you very much.
Thank you. Thank you to the Ioannis and the Rollo Davidson Trust, and it's a great honour. It's wonderful to be back in Cambridge and see so many old friends here. If the election tomorrow in the US goes badly, maybe I might stay a bit longer. But
What is that?
yeah. I think you can guess. Okay, so this is joint work with my former student, Dor Elboim, who's now a postdoc at Stanford. And it's about the interchange process, which is a random permutation valued stochastic process. But before I tell you about that, let me start with something a bit simpler, which is just card shuffling. So one way of shuffling a deck of cards is the random transposition shuffle. So you pick two cards at random and interchange their locations. And you don't need to be a great mathematician to know this isn't a very good way of shuffling a deck of cards. It'll be very slow. You do need to be a good mathematician in order to sort of answer exactly how slow it is. So actually this was a famous result in the theory of mixing times of Markov chains. So Diaconis and Shashahani introduced the idea of using representation theory to bound the mixing time. And it was also the first, or one of the first examples of the cutoff phenomena in Markov chains. Okay, and like the time, a half n log n, you should think of it as corresponding to the time it takes so that every card has been interchanged at least once. So at this time, you get essentially a uniformly random permutation. And you could ask, what does a random permutation look like? So, well, what can you ask about a permutation? I guess the main thing is sort of the structure or the size of the cycles of the permutation. And they follow a Poisson-Dirichlet distribution. So if you haven't heard this before, there's a very elegant stick-breaking description of it. You just pick a uniform random point between 0 and 1, then pick a uniform random point to the right of that, and then another one to the right of that, and so on, and split the unit interval into infinitely many segments. There'll be tending to size 0 exponentially quickly as you go to the right, but the ones on the left will be of size order 1. And then if you kind of rearrange them and put them in decreasing order of size, this is the Poisson-Dirichlet distribution. It comes up in lots of settings. And it's easy to show that this is the distribution you get, because if you ask what's the size of the cycle of the first card, say, it will be uniform on the integers between 1 and n. So that's like the first point in this stick breaking description. And then everything outside of the first cycle is just another uniform random permutation. So you get this kind of recursive structure. So this is what will happen if you do a half n log n numbers of transpositions. But you could ask, do you actually have to go that far in order to see this sort of behavior? And the answer is no. Actually, it's your former colleague Nathaniel Bereshticki, actually in his PhD thesis with Duret, showed that actually you only need n over 2 number of transpositions before you start seeing large cycles. So a bit less than n over 2 transpositions and the larger cycles are order log n, a bit more and you start getting ones of a linear size. And if this looks familiar and looks like sort of the phase transition in Erdős-Renyi random graphs, that's exactly what's happening here. If you think of drawing an edge between, say, pairs of cards, if you've done a transposition between them, then n over 2 edges is the number of edges you need to add to start seeing a giant movement. Okay, so later, although it looks like from the dates earlier, but this was just sometimes later works get published faster. Schramm showed that a more refined version of this result, where he showed if you look at the cards that are in the macroscopic cycles, which is not all of them, there'll be let's say after n transpositions, there'll be a constant fraction of the cards that haven't been transposed at all, but a constant fraction will be in the large cycles, and if you look at their relative sizes, that will be Poisson-Dirichlet distributed. And he moreover showed a dynamical version of this, where if you add transpositions one by one, you could look how do the size of the cycles change. So they'll tend to merge together or split into 2. And he showed that they follow a multiplicative coalescence and fragmentation process. So cycles merge together at rate proportional to the product of their lengths, and they split into 2 with probability proportional to the square of their length. And the Poisson-Dirichlet distribution is the uniform stationary distribution with respect to this dynamics. And actually, once you get macroscopic length cycles, it then mixes very quickly. So you only need to do sort of a large constant number of transpositions to get something close to an independent sample from the Poisson-Dirichlet distribution after that. Okay, so the process I'll talk about is like this, but with an added spatial structure to it. So rather than cards, we'll have particles on each vertex of a graph. The graph for this talk will be usually just some variety of lattice. And now our transpositions are only going to be allowed to happen on the edges of the graph. So we'll pick an edge at random, do a transposition, pick an edge at random, do a transposition, and so on. And actually, I'll be interested in doing this on infinite graphs, so I want the continuous time version of it. So on each edge, we'll have an independent rate 1 Poisson clock, and then when the clock rings, we'll do a transposition, and then we run this for time, and I'll say time beta. And at time beta, you get some random permutation, and then we're interested in the cycle structure of this permutation. So this is called the interchange process. I think it was first studied in the context of models like exclusion processes, but the context through which I was interested in it comes from a conjecture of Balintov, who is here today, and so the conjecture is that on the lattice it depends on what dimension you're in. So in dimensions 1 and 2, all of the cycles you see will always be finite. But in dimension 3 and higher, there's a phase transition. So for small values of beta, you again only see finite cycles. But after the critical value, you almost surely see infinite cycles. This is the infinite volume version of the conjecture. You could also ask about a large box in the d-dimensional lattice. And there the conjecture is that the largest cycles have a constant fraction of the volume. Or a more refined version, which would be that they also have the Poisson-Dirichlet distribution. Okay, so you might say, why dimension 1 and 2 versus dimension 3? Well, here as probabilists, the most natural, or the thing you think of is maybe random walks, a recurrent in dimension 1 and 2, transient in dimension 3 and higher. And actually what we'll see is that really studying cycles is like studying a sort of self-interacting random walk. And so if you were to believe that its recurrence or transience is similar to just a regular simple random walk, you might come to this conjecture. So, so the way I think Balint's interest came to this was in studying a model called the quantum Heisenberg ferromagnet. So if you know the Ising model, the Heisenberg model would be like that, except rather than having plus minus 1 spins, you have spins taking value in the 2 sphere. And then the Hamiltonian, rather than being the sum of pairs of spins, it would be the sum of inner product of spins on the edges. And then you take the quantum version of that. And if you sort of analyze and expand out the partition function, the interchange process pops out, except with an extra factor. So you take the permutation from the interchange process and reweight it by 2 to the number of cycles. And then the property of having large cycles or macroscopic cycles in boxes is then just directly corresponds to either spontaneous magnetization and long-range order in this quantum Heisenberg ferromagnet. So I'm not going to. So we don't have any new results about this model, but this is an important open problem in mathematical physics. By the way, the time that you run the interchange process for beta corresponds to sort of beta the inverse temperature in the Heisenberg model. So that's why beta is sort of a funny unit letter to use for time, but that's why we did that. Okay, so going back to the conjecture, you notice both when d is 1 or 2, but also for larger values of d, when beta is small, we only ever expect to see small cycles. So this part is easy to prove because I could just mark each edge as open if there's been at least one transposition on it. The Poisson processes are independent, so the marked edges will be just regular bond percolation. And if beta is small, it will be bond percolation with in the subcritical regime. And cycles must be subsets of connected components of this percolation, and therefore they'll all be finite almost surely. So, sorry?
For all dimensions?
For any dimension, yeah. So if you run it for time, let's say less than 1 over 2d, it'll always be subcritical. So, yeah. Okay, so the main challenge for this talk will be to understand what happens when beta is big. Okay, and so previously there'd been work on this on a number of different graphs. The random transposition shuffle just corresponds to the complete graph. Then later there was work by Omer Angel and Alan Hammond on trees, and more recently on the hypercube, the Hamming graph, and random regular graphs. So these are all graphs with really quite good expansion properties, more so than the lattice. And so I think that's one of the things that's made these ones a bit easier to deal with. But the result, So our results are for the lattice when the dimension is 5 or higher. And so a couple of years ago with DOR, we showed that if beta is sufficiently large, then you get infinite permutations almost, or infinite cycles almost surely, in dimension d greater than or equal to 5. And then more recently, we've studied the finite volume version of it. So if you take a box of side length L, again in dimension 5, when beta is big, then the largest cycles are of a macroscopic size, and the joint distribution follows the Poisson-Dirichlet distribution. So you may say, why dimension 5? The conjecture, should be for dimension 3 and higher. And so partly, mainly we weren't smart enough, but the reason is we were using properties of random walks that only hold in dimensions 5 and higher. So of course we know random walk is recurrent in dimension 3, but if you take two independent random walks, their traces will sort of intersect each other infinitely many times in dimension 3 and 4, but in dimension 5 there's a positive probability that they never intersect each other. Or another way of thinking about that, if you look at the walk after a long time, and then look at its future and its past, have a positive probability of not running into each other. So I've said a lot about random walks, and it's maybe not obvious where the random walks come into the interchange process. So let me describe that next. We've been calling it the cyclic walk. I know, but I mean, this is not our invention. It goes back at least as far as Balint's work. And so the idea is, rather than following all of the particles, we're just going to follow the particle that started at the origin and see where it gets moved according to the transpositions up to time beta. And up to time beta, the transpositions are independent, so it's just evolving according to a simple continuous time random walk. And then at time beta, maybe it lands somewhere else, and then maybe that's where the red particle started. So then we'll follow this red particle for time beta, and then it ends somewhere else, and then that was where, say, the green particle started, and then we'll continue following that one on. So we'll get a sort of concatenation of these paths of beta units of time. Individually, they're just independent, they're just regular simple random walk, but they're generated from the same set of Poisson processes, so they're not independent of each other. So this cyclic walk is not just simple random walk. But we'd like to show that it's kind of close enough to that, so that will be the ultimate goal. There's another representation of it where I'm going to write the graph on the x-axis, and for convenience here it will just be z. And then time will be going in the y-axis. And every time you do a transposition, I'll add a red line between the corresponding vertices. And then it's cyclic in the sense that we just repeat the same block pattern over and over again every beta units of time. And now if you want to know where the origin went, you just follow the rule where you go up, and then when you hit a red line, you cross to the other side. So this would be the path of the cyclic walk started from the origin, and at time 3 beta, it gets back to the origin, and this corresponds to, in this permutation, it's in a cycle of length 3. So one nice thing about this representation is you don't need to know all of the Poisson processes in order to generate it. So we really just needed the part of the Poisson process that's adjacent to the path of the walk, this shaded region. So then when we're generating the path from time beta to 2 beta, we've already generated the randomness in the shaded region, but what's left is independent. So let's say we did it up to time 1.5 beta. It'd be at this point, and what's sort of in front of the walk is unshaded, meaning independent. And so at this time, it will evolve according to just an independent simple random walk. So at times like this, where it's not adjacent to any shaded regions, it's sort of basically its next sort of part of the trajectory will be independent of the past. Or also, more formally, I'll say it's interacting with the past if it's sort of at distance 1 from somewhere where it's been at an integer multiple of beta in the past. And if it's not interacting with its past, then it just evolves like a regular simple random walk. Okay, so this gets us to the main sort of philosophy of the proof, which is that, okay, if the cyclic walk is behaving like a random walk, then because it's in dimension 5, it shouldn't interact too much with its past. But on the other hand, if it's not interacting too much with its past, then it should behave like a simple random walk. So this is a circular argument. So how do you turn that into a proof? Well, one sort of natural idea is to do sort of induction over timescales to try and show that this behavior holds on one timescale and then bootstrap that to show it on a larger timescale. So that will be the aim of the proof. What was I going to say? Yeah, and so as with sort of most kind of multi-scale inductions, a key thing is making the right definitions. So I have to make a few definitions now. So one is we'll call a block heavy if the amount of time the walk has spent in that block, if it's side length L, if it's spent more than L to the 2.1 time there. So I don't know if it's a block. We just want to say how much time the walk is spent in this block. If it were just regular simple random walk, assuming it entered the block, the expected amount of time would be order L squared. So the probability of spending time L to the 2.1 there should be extremely small, like e to the minus L to the 0.1 or something. So at least for simple random walk, you would not expect to see large heavy blocks coming up. Okay, and then we'll say that at time t, the walk is relaxed if I look at all of the blocks centered around its current location, if none of them are heavy. So on every scale, the walk hasn't spent too much time around its current location. Okay. And so the point of this definition is that now if I extended it with just say a regular simple random, independent simple random walk from this point, you would have a constant probability of never running into the past. It's sort of sparse enough that just from the calculations of transition probabilities, there's a good probability of sort of missing the history of it. Okay, and so if we can show similar things about the transition probability of cyclic walk, then we could show that it also escapes its past, and sort of thereby break it up into sort of independent segments. So beta is the amount of time that run the interchange process for, so it will be a large constant. So t is we've run the cyclic walk for time t, which could be much larger. Like beta is a fixed constant, t can be anything. Okay. We also have slightly different rules for boxes of small size, but let me not go into that. So the inductive hypotheses will be on timescales growing exponentially. So Tn is like 4 to the n. And the most important hypothesis will be that transition probabilities are sort of well behaved. So for a regular simple random walk up to time s, the transition probabilities are bounded by a constant times s to the minus d over 2. And we want the same to hold for the cyclic walk, but with an extra plus epsilon in the exponent to make it a bit easier. So if we knew this, then it would be enough, it would allow us to say that starting a cyclic walk from a relaxed time has a constant probability of escaping and never hitting its past, or at least up to time tn. It would also be enough to prove the main theorem as well. So if we just look at the expected number of returns to the origin and sum up those probabilities, they'd sum to something less than 1 if beta is large enough. So this will also just imply the main theorem. So we need this and a few other properties. One is that you can couple the cyclic walk very well with Brownian motion with very high probability. Another is that along the path, most times are relaxed times. So a slightly more than 90% of the time the walk will be at relaxed times. And finally, another property where we say if we start 2 cyclic walks and run them, and they don't form cycles, and they also don't merge into the same cycle, then they don't spend too much time too close to each other. So all 4 of these properties are ones that are sort of true and quite simple to prove for, say, Brownian motion or simple random walk. And so in particular, that means that the base case of the induction just follows from the fact that the cyclic walk is a simple random walk up to time beta. And then what's left is we have to show that the cyclic walk behaves close enough to a random walk, and or close enough to Brownian motion. So how do you show something is close to Brownian motion? Well, one way is to show that it's close to just a sum of IID random variables. And so, we want to show that if we take L independent cyclic walks of length 4 to the n and kind of concatenate them one after the other, so this won't be the same as a cyclic walk of length L times 4 to the n, because I'm sort of ignoring the dependencies between the two or the different walks. But what we show is that actually you can couple them with extremely high probability, this concatenated walk to a cyclic walk of length L times 4 to the n, so that the discrepancy between them is extremely small, something like L times 4 to the epsilon n. Something much, much smaller than the sort of usual fluctuations of Brownian motion. And the sort of reason why we can do this is that once you reach a relaxed time, you have a constant probability of the future then being essentially independent. Okay, but there's also a positive probability that the future hits the past and then it's not independent anymore. So what we need to show is that you quickly hit another relaxed time. Again, and then we'll try again and try. So if the red one hits the blue one, then we'll wait for another relaxed time. Try again. Hopefully the future doesn't hit the blue one. Maybe it does. But the number of trials that we need to do is will not be very big, and the total amount of time they're interacting with each other will be generally very small. And we can bound this in terms of like the total amount of time to the power of some small epsilon. So the main ingredient that we need in order to carry this out is that the walk with very high probability very quickly reaches a relaxed time. Okay. Now, there's one more ingredient we need as well, which is we need to show that the walk doesn't encounter sort of heavy regions where it spends too much time, but occasionally it will. It will just sort of go along, and there's some chance that it just sort of gets all tangled up with itself for a while. If you run the walk for long enough, this will eventually happen. So we've got to be able to sort of escape from this. So far the heuristic I've been giving you is that the walk doesn't interact with its past much, therefore it keeps evolving like a random walk. But sometimes that's false, and you've got to be able to deal with what happens when that underlying heuristic is false. You don't want to say, well, I can't sort of control what happens next, and so maybe the tangled region gets bigger and bigger and bigger and eventually comes back to the starting point, and then you close the cycle and you failed. So we want to be able to say even after a sort of bad start, we can quickly escape some region. And so if we have some sort of box on scale L, maybe we've spent a lot of time here, we want to say that there's some like exit sign that we can sort of get to, and we'll sort of, once we go through that door, we'll sort of get out of the building pretty quickly. So I'll break space up into a grid of small boxes of side length log L to the 100, so much smaller. And what we'll do is say, suppose we take this box, and I'm just going to take some well-separated points here and just start developing cyclic walks from them. If they run into each other, I'll stop revealing them. But hopefully, eventually you find one of them that sort of doesn't run into the others and wanders off and is sort of this escape route for us. And because essentially there's enough space in dimension 5, I can sort of reveal these walks and still have a good chance that they don't run into each other. And so it becomes like independent trials. And so it's very, very unlikely that none of these trials succeed. And so when we encounter one of these new green boxes for the first time, with extremely high probability, there'll be some escape route there. But if you're just sort of randomly wandering the room, you might not go out the right door. So we also need to be able to sort of connect up the entrance point with this good exit point. But because we haven't visited this box yet, if this is our first visit to it, then things in the box are just independent. The Poisson process in the box will be independent, so we'll be able to use the estimates from the inductive hypotheses to say that going from here to here is basically like the same kind of probability as you would have just for a random walk to make that transition within the box. So it will be like the side length to the power of minus some constant. So you'll have some small probability that you join up this escape route and wander off. But there's also some probability that you don't do that. The walk goes somewhere else and comes back. And so then if it fails, you can try again and keep doing independent trials until you succeed and leave this whole area. And you can count up the total number of trials until you successfully reach the exit, and the amount of time that you spend there. And essentially you don't need too many attempts, sort of something like polylogarithmic in L before you escape. And so this gives us the first of our main estimates, which is that you basically never build large heavy blocks. So any block of side length Tn to the epsilon will, except with very small probability, never be heavy, basically because you can look at the number of times you visit, visits of length r squared, you'll make at most n to the 100 of them, so that's still going to be smaller than r to the 2.1. Okay, so we don't see large heavy blocks. And now the second main estimate, this is what we need to do to sort of prove the concatenation result and complete the inductive hypotheses, is to show that after some quite small amount of time, Tn to a constant times epsilon, you'll always reach a relaxed time. Okay, and if you remember, relaxed time means it's not heavy on any scale. And we've already ruled out big scales being heavy. So we just have to worry about, are you heavy on smaller scales? And here's where we use sort of the very basic and standard construction in multi-scale arguments, which is to draw a big grid of boxes and declare some of them good and some of them bad. And okay, our definition of being good will basically be, do the inductive hypotheses more or less hold on that block? So the kind of estimates you would expect from it. And so, and the blocks will be of side length Tn to the epsilon. So the probability of a block being bad will be something like e to the minus epsilon squared n squared. So very, very small, unlikely to see any bad blocks, but it's not small enough for the next level of the inductive hypothesis, to prove the next level of the induction. And this is, a standard thing with sort of multi-scale kind of arguments. You want to get better probability bounds as you go from one level to the next. And the way you tend to do that is to say, well, as long as there's only a few bad blocks, things are still okay. So here we'll say things are okay as long as we only have a sort of large constant number of these bad subblocks. And then because there's sort of spatial independence, two blocks that are, say, not too close to each other, or let's say not adjacent, will be, the property of them being good will be independent. So the probability of seeing more than, let's say, 1 over epsilon to the 5 number of bad blocks will be small enough for the next level of our inductive hypotheses. But we have to be able to sort of survive having a few bad subblocks. But actually this isn't a problem, because our main goal is to say we, reach a relaxed time after not too long. But these bad subblocks, they're very small, and there's only a few of them. So just the total amount of time you spend in them can't be too big. So we'll just wait until we're in a good subblock. And then one of our inductive hypotheses says that in good subblocks, all of the paths should have a lot of relaxed times along them. But that really only means relaxed times with respect to the recent history of the past. The walk could have visited this block at other times in the more distant past, and we have to be able to deal with that too. But the final inductive hypothesis said that these walks don't spend too much time too close to each other. So there will be lots of times along this path where they're not too close to any of the distant history, and therefore you find relaxed times. And so that's enough to prove the concatenation and complete the sort of inductive, the next step of the induction. And so that's enough to prove the first set of results from a couple of years ago, that that you find infinite cycles in the lattice. And so the next part is to understand what happens in a finite volume. So when we have a box of side length L, it's easier to think of, it won't really matter for the results, but it's also easier to think about if it was a torus of side length L. Okay, so I could couple the cyclic walk on the infinite graph with the torus up until the point it starts sort of wrapping around and notices that it's not in the sort of infinite volume. So this will be about time L squared. So immediately the infinite volume results say you should have cycles of size at least L squared. But actually if you sort of push on the arguments a bit harder, you can show that things don't get heavy for too long and get cycles of length L to the d minus 2. After that point, there's just, the cycles are just too long, and there's sort of, the walk will run into itself too much of the time. Okay, so we can have the, so this is nice, but we want cycles of length L to the d. So the way we're going to do that is by adding in a few more transpositions. So imagine sort of just slightly playing with the value of beta, so you add in a few extra transpositions. So what happens when you add an extra transposition to the permutation? Well, if the vertices are in different cycles, then their cycles will get merged together, and you'll get a larger cycle. On the other hand, if the two vertices are in the same cycle, it will split the cycle into two parts. So if we want to understand what the effect of adding in extra transpositions, we have to understand for two large cycles what fraction of the time they're next to each other. And so this is really the main estimate that we need. It's sort of a refined transition probability kind of estimate. I want to take two walks of length a bit more than square root of the volume. So t equals L to the d over 2 plus epsilon. And I'll just reveal a first cyclic walk W1 up to that time, and then a second cyclic walk W2 up to some sort of time s that's less than that value. And then let u be a point next to W1. And now I want to say, if I run W2 for another time that's a bit more than L squared, what's the probability of being exactly at u? So assuming that u is in a fairly big cycle itself. So I want to connect these up. And the estimate that we need, at least to get the Poisson-Dirichlet calculation, is that this probability is really like 1 over L to the d. So it's the location after time L to the 2 plus epsilon is really close to just uniform. And in particular, it's even for points that are next to the path, which might be somewhat special. And that this should hold with very high probability. So our previous results with concatenation, by sort of concatenating together sort of smaller walks of different sizes, you could show that the transition probabilities are at the most L to the epsilon distance in Wasserstein distance from a uniform point. But we really want them to be exactly at a particular point. And so to do this, we need to sort of essentially smooth out the distribution. And the way we do this is along the cyclic walk, there's lots of times where if the walk could either jump to the left or jump to the right, and it wouldn't sort of affect what happens much later on. So rather than telling you, I'll sort of keep this randomness in my pocket, and then at the end say, okay, I can at each of these times throw back in the sort of random choices that I made at different points along the way, and this will be adding essentially an extra binomial random variable to the distribution, and it'll have the effect of smoothing out its location. So we can take a sort of coarse bound on the initial transition probabilities and get this more refined one. So once we know that, we can then take two paths of length t, and then look at how many times they're adjacent to each other. And by sort of using this transition probability estimate, we can estimate sort of each time we add an extra block of L to the 2 plus epsilon to W to the second walk, how many of those times it was next to W1. And then together with some martingale concentration arguments, you can show that the amount of times they're adjacent is very concentrated. Around t squared over L to the d times a constant that is basically the probability that in the infinite volume, two neighboring vertices are both in infinite components, both in infinite cycles, and they're different infinite cycles. Okay, taking something slightly bigger than L to the d over 2 is important here because essentially there's like a birthday paradox kind of calculation here. The number of times these two random walks are next to each other, if you look at should have for time 1 and on the first walk and time 2 on the second, the probability that they're next to each other should be about 1 over L to the d. And then when you have something of size more than square root of the volume, then the number of pairs of times is more than the volume, and then the concentration argument. So essentially, that will make that this is a diverging number, and therefore, and that it's concentrated. Okay, so now if I take two longer cycles, I could sort of split them up into segments of length t, and for each segment compare how many times they're adjacent. And this will say that if I have two long cycles, the number of times they're adjacent is proportional to the product of their lengths. Okay, and so now if I increase beta slightly, I'll get the chance that I merge two cycles together will be proportional to the product of its length. The probability that I split a cycle in two parts such that both parts are sort of large will be proportional to the square of its length. And so we get the same multiplicative coalescence and fragmentation process that Schramm had for the in the case of the random transposition shuffle. And so we can use this first to show that the cycles sort of merge together and grow from L cubed up to L to the 5. And then once they're at L to the 5, that they also very quickly mix and arrive at the Poisson-Dirichlet distribution. Yeah, okay. And that's all. Thanks for listening.
Is there something special about dimension 4?
So I mean, dimension 4 is where two walks, let's say you round them up for time n, the number of intersections will be just log n. So it's sort of, they intersect, but sort of barely. So you might wonder if our sort of arguments can be pushed to the case of dimension 4. I mean, well, obviously we haven't, otherwise I would have told you, but there's lots of parts where it's tricky, but it also doesn't look impossible. So on the other hand, dimension 3, the walks really run into each other a lot, or a walk will interact with its past a lot. And I think at that point you need to show that its interactions with the past are sort of like there's some cancellation. So sometimes its past bumps it to the left and sometimes to the right, and that these cancel out. And so that looks much harder to deal with. Yeah, so I mean, I can tell you some other open, so we'd like to know about dimension 3 and 4. We'd also like, in dimension 2, there's also the question of showing there's no infinite cycles. We also don't know the existence of a critical value of beta. So there's no sort of obvious monotonicity in the process. So we can't rule out the, obviously very unlikely scenario where you go from having no infinite cycles to infinite cycles, and then back to no infinite cycles, and then back to infinite cycles. So that's a bit embarrassing. And actually, Alan Hammond was able to show this on regular trees, where as long as the degree was more than like about 700 or something. And so you might wonder whether those methods would apply to the 700 dimensional lattice. But it's more complicated than on the tree, so I'm not sure about that. And then another sort of question is, can you then say something about this original quantum Heisenberg model where you want to reweight the distribution? Yeah.
Thank you. Any other questions?
In terms of float bounds, is anything better than the percolation?
Yeah, so I mean, we know that like the percolation threshold is not the right one. And I mean, partly for sort of, sometimes you'll have transpositions you do and then immediately get swapped back. And so you really shouldn't count those sorts of ones. On the other hand, I think in probably like in really high dimensions, the threshold should be sort of, like, I guess for percolation, the threshold is about 1/2D, and you would also expect beta 1/2D to be about the right asymptotics. Yeah, but we haven't tried to do that either. No, I mean we do. I mean, I think probably the way the proof is written, it's it will be like beta critical will be some astronomically large value growing astronomically with D, but it should be possible to tighten things up and get a I mean it should tend to 0 as beta is tending to infinity, but yeah, we haven't tried to do that. I would expect it to hold. Yeah. Is this being recorded, or I don't know? Yeah, no. I don't see any reason why not. I mean, it's sort of. Yeah, I mean, as long as essentially the walks are kind of mixing within the box, and sort of two long walks have the right kind of intersect, adjacencies with each other, and I don't see any reason why that shouldn't be the case in particularly dimension 4. Dimension 3, I'm less confident about speculating about.
Have you tried to equate these two to the weights of 2 to the number of?
Not successfully. We have thought about it.
Does it make it much more difficult?
I mean, so here we're really using the fact that you have independence when you sort of reveal the walk, as long as you're not interacting with the past. On the other hand, if beta is large, the dependence should be pretty weak. So we did think about a toy extension where, rather than weighting by 2 to the number of cycles, you maybe reweight by 2 to the number of short cycles. And for that, I think we can say something, but we don't know how to do the full problem at this point. Yeah, sorry to disappoint you.
If there are further questions, it's taking a rate.